So today we start looking at instantaneous rates of change. So if you were using an example of driving, if you were driving from here to Portage la Prairie, how far is it from here to Portage la Prairie? How many kilometers? 50 kilometers? Okay? And it took you an hour. You would be traveling at 50 kilometers per hour, right? Now, at any moment while you were driving, if you looked at your speedometer, it probably wouldn't stay 50 kilometers per hour. It's not like you hop in your car, set it at cruise as soon as you get in your car, it instantaneously goes to 50 kilometers an hour and you just sit there and not do anything in the traffic all the way from here to Portage la Prairie to get there within an hour. You have to stop for red lights, and then when you get on the highway, then you go faster, and you might be going at 100 kilometers per hour when you're on the highway. And what you're looking at when you look at your speedometer, that's your instantaneous rate of change. How fast are you going at that moment? When we look at the whole time, we're looking at our average rate of change, but if you look at a specific moment, you're looking at an instantaneous rate of change. Some other important definitions. We're going to find out that our instantaneous rate of change to a curve when you graph things is going to be the slope of a tangent line. And when we look at an average rate of change, that's more like looking at the slope of a secant line. So these are our definitions to start as. We're going to refine our tangent definition as we go, but often coming into grade 12, the first time that you saw a tangent line was in grade 9 when you had a tangent to a circle. And you learnt in grade 9 that a tangent line was a line that touched that circle only at one point. So we sort of have that same sort of start as what a tangent line is to begin with right now. It's a line which cuts a curve at one point. So if we have 2 points on a circle, and you draw a secant line between those 2 points, from B1 to A1, that could be shown by that black line on there. Now if you kept drawing secant lines by getting closer and closer to A1, so I've sort of shown that with the blue line here, that's a little bit closer. Then the green one is even closer. And then the red one is even closer. That slope of that secant line is an average rate of change. But as you get closer and closer and closer to A1, it gets closer to the actual tangent line at A1. And the first part of calculus is all about slopes of tangent lines, about instantaneous rates of change. So our tangent line is the instantaneous rate of change at that point. So when you look at your speedometer on your vehicle and see exactly how fast you're going at that moment, if this was graphed, your tangent line at that point would be equal to what your speedometer is saying. So what I'd like you to do on your graph, here, we've got the graph of x squared plus 1. You can put a point B1 anywhere on your parabola and put A1 at the vertex. And then draw secant lines as you get closer and closer and closer to your vertex. So as you draw your points closer and closer to that vertex, do you see that our slopes of our secants are flattening out? And they are becoming a better estimate for what the slope of, and I'll draw it in nice bright yellow. Can you see that your tangent line at that vertex would be a nice flat line just like that? And as we get closer to the vertex with our secant lines become a better estimate for our tangent line. And this is going to become the idea for how to create a derivative, for how to get an equation for the derivative. Because we can't figure out slope, right, if I just tell you 1 point. If I tell you 1, 3, what's the slope? You're like, that's not enough information. But if I gave you 2 points, you could find the slope, because then you could do rise over run. So we want to find the slope of this tangent line, this yellow one. And you might be able to just by observing say that it's equal to 0, because it's flat, it's horizontal. But if you just have that single point, it's hard to say. So if I chose another point right here, at that yellow point there is one tangent line. What's the slope of that tangent line? Well, I only have 1 point. How am I going to do that? But if I made a secant line really, really close to there, that would be a good estimate for the slope of our tangent line. And if we use the idea of limits that we did before and we get closer and closer and closer to that point, maybe we could find it exactly. So we notice that as it gets closer to that vertex, that secant line becomes horizontal, and the tangent line becomes y equals 1. Now, according to our original definition of a tangent line, cutting a circle only at one, or cutting a function only at one place, could you see that you could cut by going straight across or going straight up and down, would cut it at 1 point. Now, the tangent is only the flat one, not the one straight up and down. So we need to look at our definition and refine it a little bit. So our tangent line is a line that touches a curve at 1 point. So that's important, unlike a secant. And the slope of the tangent line is equal to that of the curve at that point. And we might even need to refine this definition a little bit further later on, because we're going to see that some tangent lines can touch it perfectly at a point, but later on it goes through the curve again. For example, if I draw this cubic function and I choose this point right here, the tangent line will be the line that goes through that and touches that at just that 1 point. But do you see that later on, it doesn't matter that it goes through that point again. So basically what we're looking at is the tangent line is the line that you get as your secants get closer and closer to joining up. That will be what your tangent line will be. So now here is the idea for getting your equation of your tangent line. You've got a part of our, maybe this is part of our parabola. You've got your 2 points A and B, and they're a little bit apart. So if we consider the x coordinate of point A to be x, and we call this distance h, does it make sense that the x coordinate of point B would be x plus h? Now you have some sort of function. Maybe this function is x squared plus 1 like we had before. But when you plug in x, your y coordinate will be y, or f of x, whatever that would be. And when you plug in x plus h, your y coordinate would be f of x plus h, whatever that would be, plugging it in. So if we would look at, again, sometimes it's easier to see things. Let's say I had x squared plus 1 here, and I chose 2 points, A and B. If point A was 1, 2, because if I plug in 1 into my function, I would get 1, 2. And this is h. This point would be 1 plus h. And if I plug that in to my equation, it would be 1 plus h all squared plus 1. That would be my y coordinate. Now, as I make this point B, fun. As I make this point B come closer and closer and closer, can you see that my h is going to get smaller and smaller and smaller? In fact, what I want to do to get my tangent line perfect is make that h get as close to 0 as possible. So what's my gradient of my secant line from A to B? It's just y2 rise over run. Does that make sense for your rise over your run? And x2 minus x1. If we simplify that, it just becomes f of x plus h, because that's your y coordinate up here, minus f of x, which is your y coordinate down here. And this length will just be h. Now I've created a little applet here. Let's zoom in even more on this to give you a sense of what's happening. And let's zoom, zoom out for just a bit. Put this here. The only thing different, I know I've been talking about moving towards point A in this example that I have right here. We're going to be moving towards point B. Wonder if I can make this bigger for you. Well, sorry that that's small. What this says right here is the slope of this tangent line that I have right now is 3.64. The slope of this blue line right now is 1.89. As I take this point C, oh, I had it there. And as I move it across, my slope here, right, the red line is 3.64, and it's small, so I'll read it to you. It's at 2.5. Now it's at 3. And as we get closer and closer, can you see how that blue line is getting closer and closer to the red line? And as that triangle gets so small that it's the same, then your secant line and your tangent line will become the same. And that slope of your secant is this f of x plus h minus f of x over h. If we let h be 0, as close as we want to A, then that secant line becomes our tangent line. And this is the definition of the derivative. A derivative is a slope of a tangent line. And we can use our idea of limits. We want our h to equal 0, so we write a limit as h gets as close to 0 as possible of our secant line. And our secant line is, the top part is just your rise, f of x plus h minus f of x, over your run, which is h. So we know this formula, we call it Newton's quotient, or the first principles of the derivative. Sometimes you'll also see it called the definition of the derivative. And another word for slope is gradient. So this new function that we find, we can call a gradient function, because by doing the derivative, you can get an equation that tells you the slopes for all the slopes of all the lines. For example, here's our y equals x squared plus 1. We already talked about knowing that here the slope would be 0. But I can tell you that if I take another point, for example, at 2, 5, I can just look at this and say, using calculus, I know that the slope of this line is 4. And if I pick another point on here, if you pick -3, 10, I can tell you that the slope of this line is -6. And so we'll be able to use calculus and derivatives and this definition to figure it out. Some notation stuff. Here are different notations of derivatives. F prime of x, y prime, and dy dx. These notations came from, this is what Leibniz used. And these were other notations that Newton used, so we have them both. So all three of those mean the same thing. It's just the derivative. So what we're going to do is we're going to use our definition of a derivative to find the gradient function, or to find the function that tells us all of the slopes at any point on this graph. So our definition, I'll rewrite it here. The limit as h goes to 0, here, I'll leave some space so I can use f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x over h. Now, one of the things that you saw the other day when you were doing limits is that you can figure out a limit if you can plug in the number, right? Like you did a question, I think something, limit as x goes to 2 of x squared. That would equal 4. And it's just a matter of plugging in 2 into the equation. So if you can plug the number into the equation, you can figure out the limit. The problem with our definition of the derivative is if we plug in 0 for h, what do we have on the bottom? We have 0. We're dividing by 0. And that's not allowed. So what's going to happen in these definitions of the derivative is we're going to plug everything into our equation. We're going to use our algebra skills to simplify. H is going to disappear from the bottom. And then we'll be able to plug in 0 for h and figure out what the gradient function is. So there's our definition of the derivative. the first thing we're always going to do is we're going to do a little bit of algebra to figure out what f of x plus h is. So what does it mean to have f of x plus h? That means that wherever there was an x in our formula, so we only have x in our formula once, in 3x squared plus 4. Wherever that x was, we are now replacing that x with x plus h. One thing you'll notice in these notes as well is I try to use a bunch of different forms of functions. So this is another way of writing function notation, just so that you get used to, maybe some textbooks use different notations, so that f colon x means the same thing as f bracket x. It's just another function notation. So all you're doing is replacing the x with x plus h. Then you're using your order of operations. Square that x plus h first. Distribute the 3. And you get this wonderfully long thing. Then, once you have that, you can go back to your limit formula, and where you had f of x plus h, you're going to write this 3x squared plus 6xh plus 3h squared plus 4. And it's going to look like this. You don't have to rewrite the definition of the derivative again. Or I'll erase it for you so you don't start rewriting it. So I replaced the f of x plus h with this. I replaced f of x with just what the original function was, and it's still all divided by h. We still have our problem, because if we plug in 0 for h, we're going to be dividing by 0. What we're going to want to try to do is look at the top. Is there anything we can simplify? And hopefully, in the end, there's going to be an h on the top that we can factor out. Because if we can factor an h out of the top after we've simplified it, can you see then it would cancel with the h on the bottom? And then we would no longer be dividing by 0. So can you see that you have some like terms? Can you see that you're going to have a 3x squared minus another 3x squared? And you're going to have a 4, and that's going to be minus another 4. So those things are going to cancel out, and on the top, we're left with just the 6xh plus the 3h squared. And now there's a common factor of the h. We can take that and factor it out. And once it's factored out, those h's can cancel. You can even draw a line through them if you like. And that's going to be key, because once you can cancel that h out on the bottom, now you're no longer dividing by 0 if you plug in 0 for h. And once that h is canceled out, now we can just apply the limit by plugging in 0 for h, and it's just equal to 6x. What does this mean? Okay, that's our gradient function. Okay, what did we just do? Well, let's graph 3x squared plus 4. 3x squared plus 4 has a vertex at 0, 4. It's opening up. It's been stretched vertically. This is the graph of 3x squared plus 4. What we did with our gradient function here is we are able to pick any point we want on 3x squared plus 4. So for example, when x is 1, we have the point 1, 7. This gradient function tells us if you want to find the tangent, the slope of the tangent at 1, All you have to do is plug in 1 into this equation. What's 6 times 1? 6. The slope of this line is 6. If I pick another point, -2, this is not going to be to scale, but -2, comma 16. At -2, comma 16, the slope of this line, if I plug in -2 for x, the slope is going to be -12. So your definition of a derivative, Newton's quotient, is called a gradient function because it's a function to find all the slopes. And if you wanted to find the vertex, you're really looking for where is the slope equal to 0, because that'll tell you right where that minimum is. And if you look at 6x, when is that equal to 0? When x is 0. So we would know the x-coordinate of our vertex from our derivative. So to start off, we use this definition of the derivative. We expand. Notice how we started? We started by figuring out what x plus h is going to be. This is where we're going to run into some problems because this was an x squared function. Eventually, we're going to be doing derivatives of x to the 7 functions. Can you imagine doing x plus h to the 7? You're going to have to go back to your binomial theorem to figure that out, or use Pascal's triangle. And it's going to be huge because it's going to have 8 terms. And it's not going to be pretty. It's going to take a long time. But that's what we're also going to develop. We're going to develop in this course ways of doing that derivative quickly so that, yes, it's going to take a long time. If I did an x plus h to the 7, I'm thinking that might be a 10 to 15 minute question to do. Okay? Then we're going to learn techniques to shave off 9 minutes and 59 seconds to 14 minutes and 59 seconds off of that 10 to 15 minutes. That's very significant. You'll be able to do it in about a second as compared to 10 to 15 minutes. Okay? We're going to develop those techniques. But right now, as part of math, to appreciate the shortcuts, we practice the long cuts. I don't know if that's a word. The long cuts for a while. So we do need to know how to use our definition of the derivative. Here is x cubed. So your first thing is you're going to have to do that f of x plus h for the x cubed and expand it. Should we do one more together? Okay. Here's the you remember Pascal's triangle? It would be a 1, 3, 3, 1 for x cubed. You remember that? 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. So if you had x plus h cubed, those would be the coefficients. And notice we've got 1, 3, 3, 1. I like the looks. You look up and go, yeah, I forgot that. So that's what takes the longest, is expanding the x plus h. Once you've expanded the x plus h, plug it into your formula. And you hope that things cancel out so you can factor out an h. What if they don't? Then you have to develop more strategies. Yes, nice. But for our first examples, they will all nicely factor out. Any polynomial that you do will always factor out nicely. In this case, the x cubes cancel out, the 1s cancel out. And on the top, every term has an h. Then if you factored out that h and canceled it out, you would be left with just 3x squared plus 3xh plus h squared. And now you can apply your limit, you can plug in 0 for h, and you get your derivative is just equal to 3x squared. Again, at this point, it's really important to keep thinking about what does this mean? If I drew the graph of x cubed plus 1, transformations, you would know that that's your x cubed graph, just moved up 1. I can now pick any point on that x cubed graph. So for example, I could choose 1, 2. And I now know that the slope of this line at 1, 2 is going to be 3. Because all I have to do is plug in 1 into my gradient function. If I wanted to find the slope at 2, 9, plug in 2 into my gradient function, and I'll know that the slope there would be 12. And so instead of having to draw secant lines closer and closer, what the definition of the derivative does is it finds a formula for finding any slope that we want at any point. And an interesting thing in this one is what's the slope going to be when x is 0? What's the slope of our tangent going to be when x is 0? The slope is going to be 0. So the x cubed graph is one of the only graph, well, it's one of few graphs that has a tangent line that actually cuts perfectly through the curve. Usually we talk about a tangent just touching a curve at the one point, but right in the middle of the x cubed graph, the tangent cuts right through it. Oh yeah, this next one is for you to try. So once you plug that into the formula, some things nicely cancel out. Once it's simplified, you could factor an h out of the top and simplify that out. And then you can apply the limit, and you'll get your derivative is 10x minus 2. So if you wanted to find out the slope when x is equal to 2, you can now just plug that in, and you find out that the slope would have been 18 at that point. We're going to start this one off. Use our definition of a derivative. So if we did our definition of a derivative and plugged it into our formula, well, plugging in x plus h is just x plus h inside the square root. And those aren't like terms. And we can't multiply the 3 inside. So we're sort of stuck at this point. And we have to use a skill that you first learned with square roots in grade 11. How do you get rid of square roots when you don't want them? Okay? Multiply them by another square root, right? Like if I had What was that called when you had a square root when you didn't want it? When did that come up? Do you remember these ones? You had a square root on the bottom and you didn't want that because somewhere someone mathematically said you shouldn't have square roots on the bottom. Right? Now, why don't you want square roots on the bottom? Did anyone ever tell you that? Well, when you had to do this by hand, which doesn't happen very, you want to change that to a decimal, what do? You go to your calculator, right? But before calculators, it was hard to divide by a square root of 5. But it wasn't hard to multiply by square roots. So they changed this and said, you know, instead of taking 6 hours to do it on the left, I can now do this in 3 hours, and that's much more efficient. Okay, we now can do that in under a second because we have our calculator. But this became important way back in the day because this was easier to do mathematically. And you develop strategies for that. But then there became those questions where you had something like that. Not only one square root on the bottom, but 2 square roots on the bottom. What did you do? You rationalized that one. How did you rationalize that one? What did you multiply by? You can tell me the numbers or you can tell me the special math word for it if you remember the math word for it. Oh, good. No one remembers the math word. Should I give you a hint? Well, I can't give you a hint in French, but it's probably very similar. But in English, it starts with C and rhymes with John Nugget. Conjugate. Oh, perfect. The conjugate is when you had the same thing with a different sign in between. Do you remember that? And that got rid of square roots. We're going to have to use that strategy in this. If I want to get rid of those square roots in the top, I'm going to have to multiply by this. So we're going to do this example, and then we're going to call class end at that time. Now, this makes things messy for a while. And when we multiply out the top, it actually makes things quite nice because it's going to become a difference of squares. But on the bottom, I'm not going to multiply the h all the way through because that h is already factored out in front, and I'm hoping that I can cancel that out. And sure enough, now that you have rationalized the numerator, the 9x's are going to cancel out, and we're left with just 9h on the top, and that will cancel out with the h on the bottom. And you can now apply that limit by plugging in 0 for h, and you get your derivative to be 3 over 2 root x. And again, we're going to develop techniques to do this one in under 5 seconds.